Hi, welcome to another lecture on business mathematics. Today we are going to talk about factoring polynomials. So we have 5 questions here and we try to answer some of them in this lecture and some of them in the next one. So first, what are the polynomials? I've written some examples. Next, we are going to look at, well, why do we study polynomials? And I'm going to mention some reasons for that. Then, why do we factor polynomials? This is a topic that we have here. Why are we after this topic? Next, how do we find the roots of polynomials or the zeros of polynomials? And then we are going to concentrate on quadratics. These are the quadratics and see what we can do with them. So you remember in the previous lecture we learned about x squared, x cubed, and so on. When you add them, you get polynomials. So polynomial, a number by itself would be simplest kind of a polynomial. That's just a constant number. Next, we have the linear polynomials. Linear polynomials, for example, 2x plus 3 or 5x plus 7 or minus 9x plus 11. These are the ones that are very familiar to everyone when we started the course with the study of these. Next are the so-called quadratics. Quadratic polynomials have an x squared in them. So, for example, 2x squared plus 3x plus 4. And then higher up than that are the cubic polynomials. Cubic polynomials, for example, 5x cubed plus 7x squared plus 9x plus 11 and so on. Sometimes instead of these names we refer to the degree of the polynomial. So instead of cubic we can say the degree is 3, meaning the largest exponent that you see is 3. For quadratic, the largest exponent that you see is 2. For linear, it's 1. We don't write the 1, but if you insist, you can have that 1 written down. Degree 0, you don't see 0, but if you insist, you can write x to power of 0. You remember x to power of 0 is 1. So we typically don't write these things because it just creates a clutter without any use. And that's how we write them. Next question is, okay, these are nice things. Why do we study them? Why do we study polynomials? Very generally speaking, is that the polynomials act as a Lego of mathematics. So I'm sure you have played with Legos as a kid. You know, you can put them together and form various structures and objects and so on. Polynomials, even though they look very simple and straightforward, when you string them along each other, you can create a very wide variety of objects with them. It's really amazing what you can do with these simple things. So they are Lego of mathematics. Well, what if you are not interested in playing Lego? How do you justify study of polynomials? Let me take you back to the previous homework you had about optimal boxes. And another justification is trajectory, like when you throw a ball up in the air, the trajectory that it takes. To explain that trajectory in its simplest case, we would need these particular polynomials, especially these quadratics. Let me just remind you again what the topic was all about. Okay, you remember in the previous lecture we talked about construction of optimal boxes. Let's go take a look at that. So we said we have a rectangular cardboard sheet, and then we cut some squares off of these corners. So here I perhaps let me see. Okay, for example, I decide to cut a square of size 1 from these corners. Then what? Well, we are doing this thing from all the four corners, but to have the control, I hide the bottom two. So if you want to cut a square of size 2 and size 3, and the maximum you can cut is 4, of course. Let's go just pick, for example, 2. What happens after we cut this thing? We fold it, we fold the flaps. So you notice that here we are preparing to fold, and when the fold is ready, we turn the flaps, and when you turn the flap, you're going to get a box. What was the issue? The issue is depending on what size you cut, the volume of your box is going to be different. The volume of the box is going to depend on how big this square is. If you cut a very small amount, well, this is going to be, of course, the original rectangular sheet, and the volume is going to be 0. If you go all the way to cutting like this, and then when you fold it, all that you get is like equivalent to a folded piece of paper. There's no volume there either. So somewhere in between, there is a sweet spot where your box is going to have the maximum volume. And the big issue was, well, how do you find that optimal box? Well, why do you care about that? Because in any business, you want to reach your optimal situation. Given the resources that you have, you want to maximize a certain objective that you have in mind. If it is revenue or whatever it is, you are working toward that goal. So part of your design criterion is to allocate your resources in a special way to achieve that. This is a mathematical version of that issue. The issue is, how do you decide on the size of the cut? Well, in the previous exercise, we showed that the volume itself is a polynomial. That's what we are studying here. The volume itself is a polynomial. And then if you want to find out what's the best design, that leads you to another polynomial. We're going to study that later. It's called derivative. You get the derivative of the polynomial that shows the volume. You get another polynomial. Then what? Then you want to find the maximum of, so here's the issue. You have we said that volume of that box you're making is going to depend on the size of the cut that you have. So x is the size of the cut on the corners of the rectangular sheet, and depending on what you choose x to be, you will have different volume. Well, what do you want to do? Well, you typically want to have the maximum volume. Where is the maximum? Maximum is as this very top. That top point separates one on the left and on the right. On the left, you are building up toward that maximum. You're going up. On the right, you're going down. And at the very top, you are staying horizontal. Well, to capture that, later on we are going to study derivative. But ahead of that time, you can say that when you are calculating the derivative, you're getting the slope of these lines. And that slope is going to be another polynomial. And up here, that slope becomes 0. And that means that polynomial has become 0. And that means that you're finding the root of that polynomial. So you see the sequence of or chain of ideas that are going to be connected to each other for us just to design a simple box. Okay, so that's one application that we have in mind. Another application we see commonly is trajectory. So for example, you watch a lot of ball games. Somebody throws a ball, somebody throws a ball, and the ball goes and lands somewhere. Somebody catches it or lands somewhere. In absence of air frictions and various other nuisances, uh, this trajectory is a polynomial. Okay, another fascinating aspect of these polynomials is that they're simply throwing a ball up in the air. You're dealing with a polynomial, and you want to find your range. You want to find out where you are going to hit here, or you want to find out how high you go, or just about anything you want to find. You have to solve for various aspects of this polynomial, and in this case that would be just finding the root of the polynomial. That is where you hit the ground, your height has become 0, and that's what the root means. You want to find when it becomes 0. To find the roots, we have to factor, and to factor, we are coming back to this lecture. So we need to learn how to play with polynomials, how to factor them, and so on. So that is the plan of action for today. Of course, beyond these simple application, optimal boxes and trajectories, there are a ton of other applications that are more advanced than what we are looking at right now. But as we said, polynomials form the Lego of mathematics. You can take these things, glue them to each other, and create fanciful structures out of just this simple looking polynomials. So before we go to factoring, let's go and see how do we multiply. So multiplication of polynomials, we have practiced things before, but factoring is just the opposite of multiplication. So if I had 2x plus 3 and I was multiplying it with, say, 5x plus 7, so this would be multiplication of polynomials. In this case, this is linear, this is linear. When I multiply them, I get a quadratic. How did we say we do this thing? By applying the law of distribution. You take 2x, the first item, and you multiply it by everything in the second parentheses, and then you take the next item. Let me put this thing in parentheses so it's perhaps clearer that way. And then 3, your second piece, and that multiplied by 5x plus 7 as well. So this is called distribution. And 2x times 5x, 2 times 5 is 10, x times x is x squared, 2x times 7 is, 2 times 7 is 14x, 3 times 5x, that is, well, 15x, and 3 times 5 is 21. You notice that the middle terms, they are same monomial part, same x in them, so you can collect similar terms. These are called similar terms. X component is the same and the number is different, so we have 2x squared plus 29x plus 21. Okay, multiplication is straightforward. It just requires patience and careful planning, and you get there. What we are after is going backward. You want to go from here back to this, and that is called factorization. Factorization is a backward operation on multiplication. Just as in driving your car backward is going to take a lot more skill than just driving it forward. Same with the case of factorization, is one level higher than multiplication itself. We have some expressions such as collecting spilt milk, taking a bottle of milk and spilling it on the floor. That's an easy thing to do, but collecting it and putting it back in the bottle is not that easy. So same issue with factorization, and so it's going to take a bit of time for us to go through this process. Let's go ahead and start with a very simple cases and gradually build ourselves to more and more complicated cases. So now we are going to look at the issue of factorization of polynomial. Factorization of polynomial, let's start with very simple case. So I suppose I have x squared, but that's all I have. So what is that? Well, that's obviously x times x. There's nothing else to do here. So what if I had 5x squared? Well, of course I can have 5x times x, or x times 5x. These are the same because multiplication can be done in any order. If you have 6x squared, you have a little bit more choices, because you can write it as 6 times 1 or 2 times 3 and so on. So I can write this as 6x times x. I could of course write it x times 6x. I could write it as 3x times 2x, or I could write it as 2x times 3x. So these are all legitimate factorizations. Now if you want to make your life a little bit harder, you can even have minus 6x times minus x. I don't write the rest of them, so you can have a minus. These are factorization into whole numbers. If you didn't care about whole numbers, you can make your life a bit more strange by having radical 6x times radical 6x. And then lots of other choices. So, well, even at this simple level, you see there are many choices, and typically what we are after is factorization into whole numbers. Occasionally negative is also okay, but these type of factorization, we rarely use them, simply because right now it's going to be too complicated to go after that, but it is there just in case you want it. Next, level up. What if I had x squared plus x? Obviously I can factor an x from, there's an x present in both of these things, so I can write it at x times plus 1. So x times x is going to be my x squared, and x times 1 is my x. And if I had 2x squared plus 3x, of course I can still factor an x, and then the big parenthesis is going to be 2x plus 3. So those are nearly trivial cases of factorization. So we are factoring a common factor. So the common factor of these two expressions is an x, and that is rather straightforward. What if there was no common factors? What if I had x squared plus 5x plus 6? Okay, the problem now becomes interesting. How can I factor this thing to two factors? First of all, the factorization that we are after, it may be there, it might not be there. So sometimes the factorization is not a simple one, is not a whole number one, and so on. So right now our assumption is that there is a factorization with whole numbers, and that's what we are after. So here we say x squared comes from an x and another x. So what is left for us to figure out what is the number in each of these two parentheses? Given that everything is positive here, I'm adding something and adding something here. So I have a number here and another number here. I have to find them such that when I multiply these two, this question mark and that question mark, when I multiply them, I have to get this 6 back. And then when I multiply this question mark with this x and that one with this one, when I put them together, I get this 5. So this question mark times the other one has to total 6. And when I add them to each other, because this one times x plus this one times that other x, has to become 5x. It means if I add these two, I get 5. So the topic sometimes is expressed like this. What are two numbers that if you add them you get 5, and if you multiply them you get 6? Sometimes we state it like this: product means multiplication. Product is 6, and this means sum. Sum means addition. Sum is 5. What are two numbers such that their product is 6, then their sum is 5? Well, with these numbers being small numbers, you probably can come up with a quick guess as to what these numbers are. If you cannot guess, you can do the following. For example, you take one of these requirements and then list all numbers that agree with that. So what are two numbers such that the product is 6? It can be 1 and 6, it can be 2 and 3, it can be 3 and 2, it can be 6 and 1, and it can be negative of these things. So we have a whole bunch of possibilities. First of all, since the sum is 5, we guess that we are only dealing with positive numbers. So that kind of rules out all of these cases. So which one of these things, where is it that the sum is 5? Well, sum of 1 and 6, that wouldn't work. 6 and 1, of course, doesn't work. But 2 and 3 or 3 and 2, they match our requirement. The sum is 5. We can write it, so we can decide to write it as x plus 2 times x plus 3, or if you wish to change the order, you can write it opposite order, is the same difference. So in this case, we succeeded in finding two numbers such that the product was 6 and the sum was 5, and we were all done. Would this method always work? Well, unfortunately, no, it doesn't always work because there could be a case that there are no whole numbers that fit your requirement. So suppose I have x squared plus 5x plus 7, and the question was, how would you factor it? So in this case, the product has to be 7 and the sum has to be 5. Well, I rummaging through my mind about all such possibilities, and I don't find any. Product 7 is 1 and 7, or negative 1 and negative 7, and none of them has the sum 5. So this one stays on the side until we have bigger guns and better tools for handling it. So it doesn't yield to our simple method right now, because the factorization is not in this nice whole numbers. There could be also the other numbers there, but this is not one of them. So we have sometimes the numbers you're dealing with have radicals in them. Sometimes the numbers are so-called complex numbers. So all sorts of things could happen. So sometimes the problems don't have a simple solution like what we expect to. Let's go ahead, take the, so this is more advanced, so it has to wait. So let's go to some other examples. Suppose I ask you to factor the following. So what do I want? I want two numbers such that the product is 9 and the sum is 6. Well, 9 has 1 and 9, 3 and 3, and the other one is same as this, and 9 and 1. And obviously, the one that matches is 3 and 3. That is x plus 3 times x plus 3. So the two numbers that we found turn out to be identical numbers. So we found some identical numbers. That's an issue that, again, we are going to have a case for it later on. When does it happen that you have identical numbers? It's just like when you have kids and the kids turn out to be twins, you have a whole set of new complications and things to deal with. In mathematics also, when the numbers turn out to be identical, same level of confusion and care has to be applied to deal with them. But right now, all we cared about was to find factorization, and here's our factorization. So if you want to abbreviate a little bit more, you can write it as x plus 3 squared, which means the same thing. Let's do another one. So suppose I have x squared, let's say x squared, say plus 2x minus 24. So for now, we are throwing in some negative numbers into the game. So I want what? I want the product to be minus 24. In the sum, to make it clear, we want the sum to be plus 2. Well, with minus 24, we have a long list of possibilities, and that's one of the drawbacks of this method. If your numbers have lots of factors in them, then you got a long list to check. Let's patiently write them. So minus 1 and 24 is a choice, minus 2 and 12. So if I multiply these two, I get minus 24. Of course, minus 3 and 8 is another choice. Minus 4 and 6 is another one. Then I have minus 6 and 4. And then I have minus 8 and 3. You see that these are numbers like just those with signs reversed. And then I have minus 12 and the 2. And I have minus 24 and 1. Thankfully, we just look at the whole numbers. But which one of these things is it that the sum is plus 2? Sum has to be plus 2. So here is the one that matches our requirement. Sum of those two numbers is plus 2. So I can write this thing as x plus 6 times x minus 4. So that was another example that we had here. Let's do another example. Suppose I have x squared minus 6x minus 16. I ask, how do you factor this thing? So in this case, we have product is minus 16 and the sum is minus 6. So how do I get minus 16? Of course, I can have minus 1 and 16, and minus 2 and 8, and minus 4 and 4, and then minus 8 and 2, and minus 16 and 1. Which one of them has a sum equal to minus 6? Well, here's my choice. So my answer is x minus 8, x plus 2. Okay. How about another example? Suppose I had minus x squared plus 6x plus 16. We are accustomed to starting with x squared. So if there is a minus, you might as well factor that one first. So I can write this as minus x squared. When I factor this, it comes out, and all the other signs are going to flip as well. Once we have it in this format, then we kick back to what we had before. So okay, now let's use that answer. So minus x minus 8 times x plus 2. Now if you want to push this minus inside any of these factors, be my guest. So for example, you could write it minus times the first one, minus x plus 8 times x plus 2. That's an option available to you, but just one of them. If you want to take this thing and push it in the second one, again, that is an option that you have, minus x minus 2. But remember, just one of them. The one that is cleaner and preferred is this style. Okay, next example, we are going to look at cases where this coefficient of x squared is something other than 1 or minus 1 and a bit more involved. So here's an example. Suppose I have 2x squared plus 7x plus 3. How do we factor this one? I'm going to teach you a method now, and then we'll have another one later on, more systematic than this, than all of these. But for now, what do we do? Step 1, take the first and last numbers and multiply them. And so say product 2 times 3, which is of course 6. And as before, this is the sum. Sum is 7. What are two numbers such that the product is 6 and the sum is 7? So for 6, of course, possibilities are 1 and 6, 2 and 3, 3 and 2, and 6 and 1. Of course, your choices are either of these two. Whichever you pick, that's fine. So for example, I pick 6 and 1. I say 7 is 6 and 1. So I write my expression, so 2x squared plus 7x plus 3. I take this 7 and write it instead 6, 6x plus 1x plus 3. Is that right? So I just put a parenthesis so that we see that what happened to 7x. We just wrote it as 6x plus 1x. Now I take 6x and glue it to the first one, and that 1x and glue it to the second one. Of course, you don't write 1x, you just write x, but just to track, I did that. Now, first two, I see that just like the very first example that we had here with this kind of factorization, we can factor by factoring out common factor. So I can take 2x out of this. It will be 2x times x plus 3. These two, that's also, well, 1x is same as x, so I just write it x plus 3. 1 times x plus 3 is just x plus 3. So I'm indicating what is the factor in front of it. It's a 1. Now I say these two is a common factor, so I write x plus 3. And then from the first, I had 2x. From the second, I have a 1. And now I have factorization of the expression. Our process became a bit more complicated than before because the coefficient of x squared was something other than 1. So again, this is a process you can go through. Later on, we are going to have a more systematic, less guessing style of factorization. But for now, that's how we are going to do it. Let's take another example. Okay, for the next example, we take the one I'm writing 6x squared plus, say, 11x plus 3. We want to factor this. So what was the process? Multiply first and last. So 6 times 3 is 18. That's going to be our product. And the sum, well, sum is the sum that you see here. So 18 the problem is that there are many choices for 18. You can factor it as 1 times 18, 2 times 9, 3 times 6, 6 times 3, 9 times 2, or of course 18 times 1. As soon as you hit the jackpot, you might stop. 2 times 9, for example. You could have picked that one. It's same thing if you pick 9 and 2. Either one, you pick one of these things because the sum matches what we want. Now what we do is we write it that 11x, the sum, we actually write it as this sum. So I write it like 2x plus 9x plus 3. Okay, so 11, I break it up. Now, first we do what in high school probably called it factorization by grouping. The first two, the common factor is 2x, and you are left with 3x plus 1. From the next two, the common factor is 3, and then you are left with 3x plus 1. No, the common factor is just this 3x plus 1, so 3x plus 1 is the common factor, and you have a contribution of 2x from the first and 3 from the next, and that is your factorization. So for small numbers, this is manageable. As your numbers become a little bit bigger than that, number of choices is going to increase, and it could be a bit tiring to try to go through them by that kind of trial and error, but still practicable for reasonable small numbers. What if our numbers are not friendly or large and such? We are going to have another method which is called the quadratic formula. Okay. We are going to continue the rest of this in the next lecture. Until then, good luck and God bless.